So in this lecture, we're going to look at logarithms. So logarithms aren't that difficult, and they're actually excellent ways in which we can deal with data and help us, make calculations much easier to work with. So we're only going to have a taste of this today, and in the next few weeks, I'm going to go much further into logarithms and show you how we can actually use them. So let's start by considering a statement. So if we have 10 to the power of 2, which equals 100, if we could say this in words, we could say 10, that could be the base, raised to the power of 2 gives 100. Now this rearrangement, this relationship can be arranged to give the same information, but with a different emphasis, i.e. to which power the base 10 must be raised to give 2, so kind of the opposite way around. So this is the form in which we call a logarithm. So this whole relationship could be abbreviated to say that log to the base 10, 100 equals 2. So this is basically changing the main point of the sentence and putting it onto this 2 instead of actually thinking about the 10, which is the base instead. So in the same way, we could say that 2 to the power of 3 or base 2 to the power of 3 equals 8 would be the same as saying log 2, 8 equals 3. Or we could say 3 to the 4 equals 81. This is getting easy now. We could say log 3, 81 equals 4. So we're just rearranging what we've got. Or perhaps another one, we could say log 25, log 5 to the 25 would quite simply equal 2. So that's basically because 5 squared equals 25. So, and finally, maybe we have something slightly more difficult where we could say log 9 to the 3 equals a half. I think we talked about this in earlier lectures. Well, we can say that that will be the same as saying 9 to a power of a half, which is its square root, equals 3. We have our base here, we have our 3 here, and we have our half here. We've just rearranged them. So effectively, we can make up this rule which says b equals a to the power of c, which is the same as saying log a, b equals c. Really quite simple. So a couple of examples. We might maybe one of the simple exam questions we might have for the 2 markers. There might be express or write log 2, 64 equals 6 in index form. So that's quite simple. We would say log 6, 64. We have our 6, and we can just use our equation to say that that would be the same as saying 2 to the power 6 equals 64. We have our 64, we have our 2, and we have our 6 here. And that's correct. Likewise, we might have something that says 5 to the 3 equals 125. And how would we transform that? Well, we would just get the numbers again and say, well, log to the base 5 equals log to the base 5 of 125 equals 3. So this is kind of quite simple. So perhaps we might get a little bit more complicated and say something, maybe complete the statement that 2 to the power of minus 3 equals question mark. And then write this in the logarithmic form. 2 to the negative 3 equals 1 divided by 8. So we know the base of the power has got to be 2, we know that. And the log has to be 3, which we know, negative 3. So we can begin to write this in a slightly different way. So we can start our log, which is to the base 2. And we know that we have 1 over 8. So that 1 over 8 then goes over here. And then we can say that that equals minus 3. So our statement would be 2 to the minus 3 equals 1 over 8. and that would be our answer. So we can also evaluate logarithms. So this is actually using them to help us with calculations. So maybe if we have something like x equals log 49, 7, then we can say that 49 to the x equals 7, which we can say that means that x equals 1 over 2. Okay, because that would be a square root, a half. Likewise, therefore we could then put that back into the equation and say log 49, 7 equals a half. So we can just fill out this equation back again. But what happens if we have a particular base of something maybe like, we say x equals log b to the 1, then we can say that b to the x equals 1, and we know that anything here which has to be equal to 1, anything to the power of 1 has to equal 0, or has to equal 0. So the answer, anything to the 0 equals 1, the answer has to be 1. So to any base, the logarithm of 1 is 0, so that would be our answer. So x would equal 0. Okay. So the laws of logarithms. So we do have some certain logarithmic rules, and these are to deal with how we actually do additions and subtractions with logarithms. So there is a little bit of proof of this, and I'll just go through it. So perhaps consider we have x equals log AB and y equals log AC. Okay, so we can write that in their different form, that a to the x equals b and a to the y equals c. So now, if we said b multiplied by c, we know that that would be the same as ax multiplied by a, by a y. But we know that that would be from our proof that that would be the same as saying a x plus y. So we can therefore say that log a b c is equal to x plus y. So that's our first log rule. Or maybe we can say this in a little bit of a neater way. We can say that log a b c equals log a b plus log a c. So that's just a simple proof by which, if we're going to add logs, this is what we need to do. So likewise, we have something similar for division. So if we were to say that b over a equals a to the x over a to the y, that would be the same as saying b over a is equal to a minus x minus y. So therefore, if we were to use logs here, we would have to say log a b divided by c, which is the same as saying x minus y. So log a b divided by c is also the same as saying log a b minus log a c. Okay, and finally we have our third log law, which looks a little bit like this, and it shows us how to deal with an expression that looks like this if we have a power to b to the n. So if this is the case, so for example, say we have something which is x equals log n, log a b to the n, this would then go to a to the x equals b to the n from our similar rules up there. Therefore, we would say that a x divided by n equals b. So x divided by n equals log a b, which goes to x equals n log a b. Therefore, log a b to the n would have to equal n log a b. So these are the proofs for the log rules. Don't worry if you haven't followed them. Just remember these are proofs, and they will be available in the on the exam formula sheet. So if we can just consolidate those, we can have three rules, which basically says log BC equals log B plus log C. Log B divided by C equals log B minus log C. And if we have log B to the power of n, that's the same as saying n log B. So these are some really simple rules, but you need to make sure you don't fall into the trap. I can name a couple of lecturers who've come and asked me these questions about logs before when they've fallen into the trap. So we'll just do a couple of examples there, and then we'll leave it at that, and that'll be the end of the lecture. So one example I might ask in the exam is express log PQ squared is going to by r in terms of log P and r, in terms of log P and log r. So what we would say here is log PQ squared square root r is the same as saying, well, first of all, let's look at this multiplication that we have here. We can say that that is the same as saying log P plus log Q plus log R, square root of R, which would be the same as saying log P plus, that's the square root, 2 log Q plus a half log R. Okay? And likewise, if we have something like simplify the expression the opposite way, which would be 3 log P plus n log Q minus 4 log R, we can do the exact same opposite thing what we've just done, but we know the rule here where we can say that that would be log P cubed plus log Q to the n minus log R to the 4, and then we can just neaten that up by saying that will be log, we can take them all into some brackets, we have a multiplication P cubed plus the P cubed, sorry, Q n all over R to the 4. And it's just as simple as that. All we're doing is following some rules. So that was your introduction to logarithms. Don't worry too much if you've not got it yet. It's just a bit of a taster, and we'll go through this again later in the statistics part of the lectures.